This paper presents a new method to fuse the classical geometry and deep learning by learning geometry-guided uncertainty. Given a geometrical problem, one can apply classical geometrical method to obtain a solution, or one can train a specific network to obtain a prediction. A natural question arises to the decision maker. Which solution should we use for a particular set of input data? Or is there a way to combine the two families of solutions in a principled way? Our intuition is that the highly confident geometric solution should be trusted more due to its well-understood rationale. But the network should take over in geometrically ill-conditioned scenarios. In this work, we focus on relative camel pose estimation, where we can apply the well-known 5-point algorithm followed by bounded adjustment to get the solution. This geometric method has the advantage in generalization, interpretability, and does not require training data. But it suffers from textureless scenes and various degeneracy and ambiguity. On the other hand, the learning method has the complementary pros and cons. The question of how to combine the two methods to trade off their relative benefits is the subject of our study. In particular, we propose to fuse the two solutions based on their respective uncertainty. The key idea lies in learning the network uncertainty together with a trainable Bayesian fusion with the geometric solution. This way, the uncertainty learning is guided by the geometric uncertainty. We use the classical way to estimate the uncertainty of the geometric solution. It estimates the covariance of the underlying Gaussian distribution by looking at the shape of the loss function around the optima. The covariance can be efficiently approximated using the Jacobian matrix. The network uncertainty is also predicted as covariance. The two solutions are then fused using Bayesian ruler, which is trivially differentiable. We compare with standard editorial uncertainty learning in isolation of geometric uncertainty, and show that the geometric guidance is the key to meaningful fusion. With the geometric guidance, the network predicts low DN uncertainty as high geometric uncertainty for DN solution to dominate in those geometrically ill-posed cases. On the other hand, the network predicts high DN uncertainty to trust the highly accurate geometric solution. In contrast, the independent learning of uncertainty retains different numerical range from geometric uncertainty, making the fusion meaningless. Here is more detailed architecture. We learn appearance feature by a ResNet, and then geometrical feature by a self-attention graph neural network. The motion and uncertainty are predicted by MLPs, and then fused with the geometric solution. The fused solution receives the supervision for training. The fusion is non-trivial due to the manifold nature of translation, which also introduces discontinuity in representation. We carefully choose motion parameterization and propose the circular fusion to address these challenges. We evaluate on a benchmark dataset demo and test our fusion framework with both shifts and superglue for correspondence. Our method also performs both the pure geometric method and recent learning methods, especially when it's combined with superglue. We analyze how the fusion overall improves the performance. It can be seen that the fusion retains highly accurate geometric solution and significantly improves those highly uncertain geometric solutions. We qualitatively demonstrate the performance improvement on those geometrically ill-posed cases, including textureless scenes, near-plane degeneracy, and bas relief ambiguity. To conclude, we present a principled trainable way to fuse geometry and deep learning by learning the geometry-guided uncertainty. We envision that our framework is broadly applicable for other geometrical problems.